Welcome to the Deep Dive. We're the show that helps you get truly well informed by digging through stacks of sources on fascinating topics. And today, wow, we're taking a journey spanning like 500 years. Think about it, from the incredible Gothic cathedrals reaching for the sky all the way to the super smart connected buildings we're starting to see now. For almost all that time, the way we talked about construction, the language was basically flat. Two-dimensional drawings, paper plans, and you had this meticulous, sometimes really painstaking process of turning those lines on paper into actual towering structures. It was human ingenuity at its finest, really.
Hmm.
But then things started to change dramatically. Today, we're diving deep into what people are calling the BIM Revolution. It's this huge shift away from those traditional paper plans, those static lines, towards intelligent 3D models and, well, actually, a lot more than just 3D. The practice, it's called Building Information Modeling, or BIM for short. To guide us through this transformation, we're drawing on some key texts, including the really authoritative BIM handbook, but also pulling from a bunch of other sources that really paint the picture of the before and after. Our mission for you, our listener, is pretty straightforward. We want to give you a shortcut, a way to get genuinely well informed about this massive paradigm shift. We're going to trace the history, unpack the core ideas, things like parametric modeling, and these really interesting dimensions of BIM. We'll look at how it's actually being used, the challenges people face trying to adopt it, and honestly, the pretty exciting future it points towards. So get ready for some, hopefully, some aha moments, because this isn't just a tech update. It's fundamentally changing how we design buildings, how we build them, and even how we run them day to day. So to really get why BIM is such a revolution, we first need to appreciate what came before it. That 5th-century reign of 2D. For literally hundreds of years, architects, engineers, builders, they all worked within this world defined by flat representations. Plans, sections, elevations. That was the universal language. It was the standard way to communicate everything, from a simple house to the most mind-bogglingly complex structures ever built. I mean, just stop and think about the sheer ingenuity involved back then. Picture those massive Gothic cathedrals still standing today, right? Incredible feats of engineering, of art. Or think about Brunellesi's dome in Florence. 15th century, a structural marvel that still blows people away. These weren't just built with skill. They were dreamt up, designed, and crucially, communicated through drawings. Okay, sure, also physical models and the builder's own amazing craft. But the drawings were key. There's a great point from the architectural critic Rainer Banham. He said, all great architecture has been conceptual, has been image making. He really pushed back against this idea, this insidious myth, he called it, that amazing buildings like cathedrals just sort of grew organically, unconsciously, no way. Even before computers, designers had a clear vision, a concept. And that vision was then painstakingly translated onto 2D drawings so it could actually be built. It really shows you how powerful human creativity and communication can be, that you could build such complex 3D things from flat paper for so long. It was the best system they had, and honestly, it worked remarkably well in its own way.
You've really captured the lasting power of 2D. It was the foundation for centuries, and like you said, it worked. It enabled incredible things. But it's just as important to understand that, yeah, while it worked, it definitely came with built-in limitations, often frustrating ones. And these limitations, they often showed up as, well, inefficiencies, misunderstandings, and sometimes pretty serious disputes and costs on projects. One of the biggest issues, and it really contributed to friction, was how fragmented information was, how it created these silos. Traditional practice in the BIM handbook really spells this out. It often separated the design intent drawings, the architect's big picture, the engineer's main systems, from the detailed construction coordination drawings. These finer details, like exactly how a pipe fits around a beam or how two components connect precisely, they were often worked out later. In separate construction coordination documents or complex shop drawings, usually done by the trades themselves, the subcontractors.
Ah, okay, so the designer hands over the concept, and then someone else figures out the nitty-gritty of how to build it, using different drawings.
Exactly. And that separation wasn't just about workflow. It was partly a legal thing, a way to uh, indemnify designers from liability for coordination problems. It created these distinct roles, distinct responsibilities, and sometimes, yeah, almost adversarial relationships.
I can see how that might cause problems, like passing the buck, almost.
A little bit, yeah.
Yeah.
And it leads straight into the massive challenge of coordination. Just picture it. You've got big plumbing pipes, complex electrical conduits, hefty structural beams, all needing to fit perfectly into the same, often tight physical space. In the old 2D world, each of those might be on a different drawing set, maybe even designed by different teams, trying to mentally overlay them or physically on a light table.
Hoping nothing clashes.
Exactly. Hoping nothing clashes. It was a constant source of errors. It was like trying to assemble something complex with 3 different sets of instructions that weren't designed to work together. And when those clashes weren't caught until you were actually building, when the duct literally hits the beam well, that meant costly rework, major delays, and just huge frustration for everyone. It was very reactive. Problem solving after the problem happened. And beyond just coordination, so many processes were just intensely manual. Think about quantity takeoffs for estimating costs.
Oh, yeah, literally counting things off drawing.
Literally counting every single brick, every light fixture, measuring square footage with a ruler and calculator across potentially hundreds of drawings. Tedious doesn't even begin to cover it. Or trying to do clash detection manually. Skilled people would stare at overlaid drawings, just visually hunting for potential problems.
Sounds like a recipe for missing things.
Oh, absolutely. And then think about revisions. Any change meant manually updating potentially dozens of drawing sheets. Hugely prone to human error. Things get missed. Dimensions don't get updated everywhere. So that was the environment. That was the ecosystem built on paper, built on these traditional silos and manual processes that BIM stepped into. It promised a completely different way, a digital transformation.
Okay, so fast forward a bit, late 20th century. Computers arrive on the scene and start, chipping away at this 2D dominance. The first big step was computer-aided design, CAD. And yeah, CAD made drafting faster, definitely more precise, cleaner than old ink drawings. But fundamentally, it was still about drawing lines, right? Just doing it on a screen instead of paper. You were still creating those 2D plans, sections, elevations, just digitally. It helped efficiency, sure, but it wasn't a total rethink. But even that early digital era, it started to hint at something bigger. One of the sources we looked at, Designing Reality, talks about this foreshadowing a third digital revolution. The idea was moving towards digitizing not just the description of an object, like a drawing, but the actual construction of it. Moving beyond just drawing a building to, digital creation, where the data itself could drive how something is made. That was a really crucial mental leap, sort of laying groundwork. And that something bigger is BIM. Now, lots of people hear BIM and they think, oh, it's a 3D model, like we see in architectural visualizations. But that feels like an oversimplification, right? Like saying a smartphone is just a portable phone. So let's really unpack this. What is BIM exactly? And how is it so fundamentally different from just a fancy 3D picture? What's the secret sauce?
That is the absolute key distinction. And you're right, it's easy to misunderstand. BIM includes sophisticated 3D geometry, absolutely. But it's so much more than just visualization. Think about it less like drawing a wall and more like building a digital version of that wall that actually knows it's a wall. The CMAA Standards of Practice puts it really well. BIM is an intelligent digital database. Objects, spaces, characteristics of the building, they're all defined and stored in this database. It's packed with information.
A database, okay, not just graphics.
Exactly. That's what makes it an intelligent model. It's a virtual representation of a physical facility, yes, but one that can support deep analysis, simulations, collaboration. Not just look pretty. Every single element in a BIM model, a wall, a door, a pipe, a beam, isn't just a shape. It carries data. Rich, connected data. So that wall object, it might know its material, concrete, drywall, whatever. It might know the manufacturer, the cost per square foot, its thermal properties for energy calculations, its fire rating according to code, even a unique ID for tracking through construction and maintenance.
Wow, so every piece is like a little data package.
Precisely. It's a smart object within a smart model. Think about something like fire ratings from the International Building Code. That data can be embedded right into the wall object, making code compliance checks way easier. And the engine driving this intelligence is largely what's called parametric modeling. This is where the real magic happens, and it takes us light years beyond traditional CAD. Instead of drawing lines that just represent a wall, in BIM you place an intelligent wall object. It inherently understands it's a wall. It has properties height, thickness, material, and crucially, it understands its relationships to other elements, like floors, ceilings, adjacent walls.
So the parts know how they fit together.
Yes. It captures the design intent, not just the final shape, but the rules and relationships behind it. This makes creating and editing the model vastly easier. And critically, as the CMAA guide points out, this massively reduces coordination errors compared to old 2D CAD. Why? Because those relationships, that intelligence, it's built into the model. It's not reliant on someone manually checking dozens of separate drawings.
Okay, so if I say move a wall.
If you move a wall, connected elements like the floor, the ceiling, maybe even ducts running near it, they can often automatically adjust based on the rules you set. They maintain their defined relationships. This drastically cuts the chances of a costly clash showing up later on site. It's like having a digital assistant constantly keeping things synced up as you design.
That idea of built-in intelligence, objects knowing what they are and how they relate, that's really powerful. So this term parametric modeling, let's break it down a bit more. What does it actually feel like for a designer using it day to day? How does it add that intelligence you described? Can you give us the simple version?
Okay, think of it like this. Imagine smart Lego bricks versus just drawing lines. A regular Lego brick isn't just a block, right? It has studs, holes. It knows how to connect to other bricks. When you snap a wall brick onto a floor brick, they fit. They have a relationship. Now imagine with parametric modeling. If you stretch that wall brick longer, the window brick inside it doesn't just hang there awkwardly. No, it automatically recalculates its position. Maybe it stays centered. Maybe it keeps a certain distance from the end based on the rules, the parameters you set for it. That's the core idea. Smart rule-based components.
Ah, I get it. The pieces react to changes based on predefined rules.
Exactly. The components aren't static shapes. They're dynamic, intelligent objects with defined relationships and properties. So if you change one parameter, maybe the height of that wall or the size of a door or even the type of steel beam you're using, all the related elements can update automatically. Window openings might adjust, structural supports might shift, even the cost estimate associated with that wall could update instantly. This flexibility is just. It's a massive advantage for trying out different design ideas, iterating quickly, and crucially, catching errors early. Errors that would be incredibly hard, maybe impossible, to spot in a stack of 2D drawings.
So it's like a living digital prototype.
That's a great way to put it. A living prototype that actively responds as you design, giving you immediate feedback. And what's really fascinating, where BIM gets even more powerful, is how it extends beyond just the 3D geometry. It pulls in these other crucial project dimensions, time and cost. Let's start with 4D BIM. This brings the element of time right into the model. A 4D BIM tool doesn't just show you the finished building, it actually dynamically links the project schedule, typically a CPM schedule, to the 3D objects in the model.
Okay, CPM, that's the critical path method, right? The sequence of tasks that dictates the project length.
Exactly. So 4D BIM takes that critical path, that sequence of activities, and visually connects it to the building components themselves. The model becomes a living timeline. It creates this graphically rich, animated view of how the construction is planned to unfold over time. You can literally hit play and watch a virtual construction sequence.
Wow, like a time-lapse video before anything is even built.
Precisely. You can see which parts go up when, what materials arrive, where cranes need to be. It's incredibly powerful for phasing complex jobs, for coordinating different trades, and just communicating the plan clearly to everyone involved, from the client down to the site crew. And it lets you run simulated what-if scenarios. What if we build this section first? What if that delivery is delayed? You can test different sequences, potential bottlenecks, like maybe a truck can't access the site during week 10 because another crew is working there.
Yeah.
You catch these time clashes, not just spatial ones.
Preventing delays before they happen.
Yes, exactly. Optimizing the schedule before you even break ground. That saves huge amounts of time and money compared to finding out the hard way. And it makes traditional CPM scheduling much more dynamic, much more visual, which is vital because, as construction managers know, that critical path can definitely change as the project progresses. 4D helps you see and manage that. Then you have 5D BIM. This layer integrates cost. With 5D, every single element in that intelligent model can be linked to its actual cost, materials, labor, equipment, everything. So that parametric wall object, it doesn't just know its dimensions and material. It knows its cost per square foot, how many hours it takes to install, the price of the drywall.
So quantity takeoffs become automatic?
Essentially, yes. It allows for parametric and dynamic quantity takeoffs for your bill of materials. This gives you a much more accurate cost estimate, much faster than manual methods. It tackles that incredibly tedious and error-prone task we talked about earlier. And the real benefit here, it frees up the estimators. They spend less time on the quantity takeoff, just counting things, and more time spent on performing cost estimate analysis.
So they can focus on the bigger picture, like value engineering.
Exactly. They can analyze the cost implications of different design choices, compare material options, optimize the budget strategically. Imagine being able to instantly see how switching from brick to metal cladding impacts the total project cost. This is super valuable, especially for projects with unit price contracts, which you often see in heavy civil work, like highways or tunnels. In those jobs, estimating exact quantities of things like excavated earth or lengths of pipe beforehand is really tough. 5D BIM's precise quantification and rapid iteration makes budgeting and managing costs on those complex projects much, much more effective.
Okay, one of the things you hear about constantly with BIM, almost like its killer app, is clash detection. Anyone who's dealt with construction or even just home renovation snafus knows the pain of finding out a pipe is where a wire needs to go. This sounds like a game changer. Why is it such a big deal?
It absolutely is a game changer, especially with how complex modern buildings are, crammed with all sorts of systems. Because the BIM model represents virtual true space, a precise digital twin of the physical reality. The software lets teams automatically check for interferences by searching for intersecting volumes. So it finds, with incredible accuracy, exactly where, say, a big HVAC duct is modeled to run right through a main structural beam, or where plumbing pipes and electrical conduits are trying to occupy the same space.
Things that would be a nightmare to discover during construction.
A complete nightmare. In the old 2D world, catching something like that beforehand, it was really hard. It relied on experienced people carefully reviewing stacks of drawings, trying to visualize it all in 3D in their heads. Very easy to miss things. So clash detection allows for truly proactive problem solving. Teams can resolve conflicts between systems in the virtual world before they become costly rework in the field.
Fixing it with mouse clicks instead of jackhammers.
Exactly. Instead of finding the clash on-site, stopping work, tearing things out, redesigning on the fly, ordering new materials, all hugely expensive and time-consuming, you identify and fix it digitally. Often this involves using specialized third-party applications. These tools can bring together models from different disciplines, architectural, structural, MEP, mechanical, electrical, plumbing, into one federated model and run clash tests across everything.
So everyone's models get checked against each other.
Right. It finds clashes between disciplines, which were often the hardest to spot before. Imagine the cost savings, the time savings, from avoiding just one major clash between, say, structural steel and the main ventilation system. Finding it digitally versus finding it physically. It's night and day. This is where BIM delivers massive tangible value. But, looking bigger picture, BIM isn't just about preventing problems. It's really about enabling better buildings from the get-go. Its analytical power goes way beyond just finding clashes. BIM supports a whole range of sophisticated qualitative and quantitative analyses. We're talking structural analysis, detailed energy consumption simulations, precise daylighting studies to see how natural light fills a space, lots of different performance metrics.
So you can test how the building will perform before it's built.
Exactly. Designers can simulate how different window types affect heating and cooling loads, or calculate the energy performance of various insulation options, or see exactly how sunlight will move through rooms at different times of day and year. It shifts design decisions from being based on rules of thumb or experience alone to being driven by hard data and simulation. And this is absolutely crucial for designing today's high-performance buildings. Achieving specific targets for operational energy efficiencies, for example, typically relies heavily on accurate modeling. BIM feeds directly into these advanced energy models. It helps designers make informed choices about sustainable materials, like specifying low-E coatings on windows to reduce heat gain or loss, or selecting high-efficacy lighting systems. As one source, Sustainable Construction, points out, these choices significantly cut down on energy use and the building's environmental impact. The detailed information inside the BIM model makes these kinds of optimization decisions possible right from the start.
Rather than trying to fix it later or just hoping for the best.
Precisely. So what for you, the listener? It means the buildings you use every day, your office, the hospital, the airport, maybe even your next home, are increasingly designed to be more energy efficient, more comfortable, healthier to be in, and just generally more environmentally responsible. And a lot of that is thanks to the analytical power that BIM brings to the design process. It's helping make our built world smarter and more sustainable.
Okay, this is where it gets really interesting for me. We've talked about the improved processes, avoiding problems, better designs, but what about the bottom line? What kind of actual tangible returns are companies seeing when they invest in BIM? Is there a measurable ROI?
Oh, definitely. The economic drivers are significant, and they spread across the whole project lifecycle, benefiting different players. The BIM handbook makes a really interesting point. It argues that purely in terms of financial gain, subcontractors who fabricate complex, engineered-to-order components, think intricate ductwork systems, pre-assembled wall panels, custom steel structures, they might actually gain more from BIM than any other participant.
More than the architects or the main builders. Why is that?
Because BIM gives them exactly what they need. Incredibly precise, data-rich digital models that can often plug directly into their automated manufacturing machinery. CNC machines, robotic welders, etc. This lets them achieve efficiencies similar to what you see in industries like automotive manufacturing, where computer-aided manufacturing is standard. They can optimize material use, minimize waste, reduce assembly time. Basically, leverage digital data for super efficient prefabrication off-site. That cuts their costs and improves quality dramatically. And then, looking more broadly at cost and time savings for the whole project, BIM definitely leads to significant pre-construction reduction. By catching clashes and coordination issues virtually before construction starts, you dramatically reduce the need for costly rework and redesigns later on. Imagine finding 80% fewer conflicts on site. The savings in time, materials, and labor are huge. And like we touched on with 5D BIM, automating those quantity takeoffs. It saves estimators massive amounts of time they can then spend on higher value stuff like strategic cost analysis, value engineering, exploring options, rather than just counting things. That translates directly into better budget control and more predictable project outcomes.
Makes sense. More time thinking, less time counting.
Exactly. And the benefits don't even stop when the building's finished. There's a process called building commissioning.
Right. That's checking that everything works as designed. HVAC, lights, plumbing.
Precisely. It's a rigorous verification process, ensuring the owner gets the building they paid for, with all systems running optimally according to the design intent. Now, commissioning itself isn't purely a BIM function, but BIM provides the essential backbone for it. That comprehensive, accurate data model is invaluable for testing, validating, and documenting system performance. And the source Sustainable Construction notes that the long-term savings due to building commissioning are truly staggering. Ensuring systems run efficiently from day one saves enormous amounts on energy and maintenance costs over the building's entire lifespan. So BIM, by supporting effective commissioning, contributes to those massive long-term operational savings for the building owner. It's like a final quality check that pays dividends for decades.
Okay, this all sounds genuinely revolutionary, a massive leap forward. But changing habits built up over centuries, shifting from paper and pencil thinking to this kind of digital intelligence, that cannot be easy. What are the real-world hurdles? What are the biggest challenges people and companies face when they actually try to implement BIM? It's clearly more than just buying some new software, right?
You've absolutely nailed the most crucial point there. It raises a really important question. The tech itself is exciting, powerful, yes, but it's only half the battle. Implementing BIM requires a huge cultural shift, a huge skill set shift within the entire AEC industry, architecture, engineering, and construction. It's fundamentally a human challenge, maybe even more than a technical one. For instance, the BIM handbook points out that we're likely looking at a decline of the traditional role of drafting.
Yeah, I can see that. If the model has the intelligence, you need fewer people just drawing lines.
Exactly. And for people who've built their careers on that skill, that can be really unsettling. Worries about job security, about becoming obsolete. It's understandable. So companies have to plan for this. They need to focus on reskilling the workforce, training people to become effective BIM operators or BIM managers, developing new skills in data management, parametric thinking, using complex collaborative software. And companies need to be really sensitive to this in their adoption plan, not just for morale, but because if people resist, if they don't buy in, if they aren't trained properly, the whole BIM implementation can stall or even fail. It's classic organizational change management. Leadership is also absolutely critical. Construction managers, for example, have a key role in educating its own personnel and the rest of the project team about how to use BIM effectively. And it's not just about clicking buttons in the software. It's about fostering a completely new mindset. BIM thrives on, really demands a collaborative culture.
Moving away from those silos we talked about earlier.
Completely. Moving away from that old model where designers worked in isolation and just kind of threw drawings over the wall to the next discipline, the PMBOK guide puts it really well. Project teams do best when there's shared responsibility toward the project goal. That creates a healthy and vibrant environment. So BIM requires actively breaking down those traditional barriers between architects, engineers, contractors, subcontractors, encouraging true integration, shared data, shared goals, right from the very beginning. It's a massive cultural shift from the sometimes adversarial relationships of the past. And then there's the whole legal and contractual side. The frameworks we've used for decades were built for that 2D fragmented world. They often just don't fit BIM's integrated data-centric approach.
Like who owns the model? Who's liable if data is wrong?
Exactly those kinds of questions. Imagine a contract based on the drawings being the final word, when the drawing is now this complex, evolving digital model shared by multiple parties. So, as the BIM handbook states, we need new contract structures. Contracts that clearly define responsibilities for model creation, data accuracy, intellectual property rights, liability, all within this shared BIM environment. Without the legal side catching up, you can get into serious disputes really quickly. In traditional project setups like design bid build, you often need a dedicated BIM integrator role.
Someone whose job it is to manage the combined model.
Pretty much. It could be the architect, an engineer, the builder, a CM, or even a specialist consultant. Their job is to take the models from different sources, architectural, structural, MEP, combine them, run clash detection, manage the process, and ensure everyone is working from the same coordinated digital information. It helps bridge those traditional gaps. Getting the responsibilities clear in those new contracts is vital. Things like the division of responsibility among team members at different project stages need to be spelled out. Issues around data sharing, exclusivity clauses, who can use the model for what purpose, all need resolving to avoid conflicts later on. Ultimately, every project is unique. As the PMBO guide says, tailoring is necessary because each project exists in a particular context. So you need a flexible, adaptable approach to contracts and workflows, one that truly embraces collaboration. The whole legal and contractual side of the industry is still learning and adapting to BIM.
So we've seen how BIM is changing things right now. But looking ahead, where is this all leading? If BIM is the foundation, what's the future look like? How will things actually be made differently because of this technology?
Yeah, this is where it gets really exciting. BIM truly is the foundational technology for some incredibly advanced practices, particularly in what's called digital fabrication. This isn't just designing digitally and then printing plans for humans to build from. It's about closing that loop between the digital design and the physical creation, moving directly from the bits in the computer to the atoms of the building. Designing reality describes this really well. It's about computers controlling machines that make things. It enables the digitization of not just the description, but also the actual construction.
So robots on the construction site, guided by the BIM model.
It's exactly. Or highly automated prefabrication in factories. Imagine robotic arms laying bricks precisely according to the model's coordinates, or welding complex steel connections autonomously. It sounds futuristic, but it's starting to happen. The BIM model provides the precise instructions those machines need, and this is happening at different scales. You have personal fabrication, where individuals can become creators, using 3D printers or small CNC machines connected to design software to make custom parts or objects locally. Think about milling your own circuit board traces directly from a design file, or using robotic pick-and-place machines for electronics assembly based on digital layouts. Then scale that up industrially. Fully automated production lines for building components, entire modules assembled by robots, all driven by the rich data within the BIM model. It really embodies this profound idea of evolving bits to arrange atoms and vice versa. It's fundamentally reshaping manufacturing and construction, blurring those lines between design and making. And beyond fabrication, BIM is also the absolute cornerstone for another really powerful concept, the digital twin.
Okay, digital twin. That sounds like the ultimate evolution of the BIM model.
It really is. Think of it as taking that detailed virtual representation we talked about, the intelligent model, and making it live. A digital twin is a virtual replica that is continuously, dynamically updated with real-world data. This data streams in from an ecosystem of sensors embedded throughout the physical building or even across an entire city.
So the digital model constantly mirrors what's happening in the real world.
Exactly. Real-time data flows back into the digital twin. Imagine a digital replica of your office building that knows the current temperature in every zone, the real-time energy use of the HVAC system, the occupancy levels detected by sensors, all updated constantly. It's a living, breathing digital mirror. And this connects directly to the bigger vision of smart cities. As the City of Tomorrow describes it, you have this network of sensors gathering urban information traffic flow, air quality, energy demand, waste bin levels, and then network-enabled actuators can respond. Things like adjusting traffic lights, optimizing bus routes, directing waste collection trucks more efficiently. We're heading towards these complex, data-driven feedback loops. Cities become like reflexive test beds, constantly learning and adapting based on real-time information, connecting the digital and physical realms.
Using data to make the city run better.
Precisely. And that flow of urban big data is crucial. As Thinking in Systems wisely points out, information is what holds systems together. But if that information is biased, late, or missing, the feedback loops break down. Digital twins aim to perfect that information flow for smarter real-time decisions, predictive maintenance on infrastructure, optimized operations, even better emergency response. And the ultimate promise here, an amazing enhancement of human experience. Better health outcomes, improved education delivery, increased productivity, all enabled by creating environments from single buildings to whole cities that are constantly learning, adapting, and intelligently responding to the needs of the people within them and the conditions around them. It's about building a future that's not just smart, but truly responsive and self-optimizing.
Wow, what a journey we've taken today. From those 500-year-old 2D blueprints, the foundation of everything from Renaissance domes to modern skyscrapers, really showing the power of human communication, all the way to this incredibly dynamic, data-packed world of building information modeling. We've seen BIM isn't just about fancier models, it's about enabling smarter decisions, driving much more efficient processes, and really pushing for a truly collaborative way of building, finally breaking down those old, inefficient silos. And this whole revolution, it doesn't just affect the architects and engineers. It impacts the very buildings around us, the spaces you live in, work in, travel through. They're being shaped by this intelligence in ways we might not even notice, becoming more efficient, safer, more integrated than ever before. From catching those costly clashes before they happen on site to fine-tuning a building's energy use for decades to come, BIM is quietly but powerfully reshaping our physical world, making it smarter, more sustainable. So here's a final thought for you to chew on, something to consider as you go about your day. If buildings are becoming, as the PMBOK guide suggests, these complex, multifaceted entities that act like systems within dynamic environments. And if they're generating huge amounts of urban big data, as the city of tomorrow describes, what kinds of new learning or adaptation might buildings themselves start to show in the future? As they become these truly intelligent digital twins, constantly fed data, maybe even equipped with AI and robotic capabilities, what does it mean for a building to learn from its own performance data and actually adapt over time? Almost like a living system within our smart cities, perhaps anticipating our needs or optimizing itself without direct human commands. What does that future look like?